Again, I'm going to be switching back between two windows. Brief introduction, and then accompanied with screenshots of the commands in case it's not working for you, what in theory it should look like, and then sometimes you'll have to scroll through the output. So I will do some screenshots in between, trying to make it as easy as possible for everybody involved. Okay, so RepeatMasker, written in 1996, I believe, by Arjen Smit, and improved upon since its inception. It's been improved upon many different ways. We're working on refactoring it currently. Refactoring, reconfiguring, whatever reword is your favorite, to implement a couple new programs to make it even more sensitive, faster, better, kind of a thing. But I still think it's worth going over the input, how it runs, and then understanding the output. I've gotten a lot of questions working on different projects. How does it run? Why does it matter if I use -species -lib? What does this output mean? Why do I care about the ID numbers? So I'd like to highlight some of those. Hopefully. Okay, so as with the last, you can see there's clearly a format I follow with my previous tutorial in this one. There are 4 parts to this. We're going to talk about the input, just getting started on the command line, understanding the output, and then some post-processing. Okay. So in terms of the input, I work with the philosophy garbage in, garbage out. If you have a poor quality genome and a poor quality library, RepeatMasker is very sophisticated, but it is not a magical solution to all of your problems. Okay, so these are things you need to consider when you're trying, because this will influence the output. So, but the 2 files that are required, I just said in terms of the high quality, hopefully that you have, are the genome and a library. That's all you need. The simplest RepeatMasker run is just calling RepeatMasker and you have your library and run the defaults. That's it. I have supplied some demo files. You should be able to find those once we get launched with a Docker image. So again, if you have a higher quality genome, assembled from long reads, supplemented with coverage or short reads, that's fantastic. So these are things to consider, before you start to try and say RepeatMasker is crap. I don't understand the output. Well, what was the input first? So in general, I talked about DFAM. We have lots of raw libraries, but if you want higher quality output and more understandable output, you're going to want higher quality input libraries. So if you have higher quality input libraries, classification will be easier to follow versus for like whatever classification system you're currently following. And these are used for fragment joining. So if it's like consistent classification used for fragment joining and part of RepeatMasker processing. Having a non-redundant library, much easier if you don't have a redundant library for post-processing and confusing annotations. Also, if you have highly fragmented libraries that might be produced by, say, a de novo output, which Repeat Modeler can be guilty of as well, you might have several annotations that are supposed to belong to the same one. If you don't have it, if you haven't extended your library or you haven't done any fragment joining of your library. Okay. So again, your input genome FASTA format and your input library. Your input library can either be FASTA, it can be an H5. I talked about H5 format for the DFAM demo, or an EMBL format. And I believe that Kenji did a very nice intro into what EMBL really looks like. I think I just did a snapshot. Okay, so now switching over. So hopefully you've logged in to the virtual machine. Okay, I've already logged in to the virtual machine. So looks like this, right? We're going to get started with the Docker image. So you're going to change directories to TE tools. Okay. I like to do LSLTR. I just also think it's nice to have LTR just always inserted into everyday commands. So then what you're going to do to get the Docker image started is // dfam te tools.sh and hit enter. And you're good. To start RepeatMasker and to look at all the options, you should just be able to type in RepeatMasker, capital R, capital M, and all of these will pop up. Okay, now this is obviously the very end of the options. There are several other options, which I'm going to switch back to the presentation. Okay, so you should see all of the options. You should be able to see which version of RepeatMasker. Is it the libraries associated with it, DFAM 3.6 plus rep-based libraries, which was part of the initial initial DFAM. And you're going to get a synopsis of RepeatMasker runs. So I've here like the very simplistic run, as I said. The default settings are for masking repeats in a primate sequences. So all you need is RepeatMasker, the name you just called, your sequence file, and it'll run. No other options. Now, there are so many other options to consider, and it really might seem daunting, but it's worth reading through them at least once. Making a list. Do I care if it's more sensitive? If it's a faster search, I'm just trying to look for a brief repeat search. Maybe you want to do a quicker search. Won't be as sensitive, but it'll be fast. You get an idea. Do you care about the engine, about what you're using? So here, this option here, well, yeah, I guess it works. So that will influence the sensitivity. For example, Hummer is a more sensitive search engine than Hummer. I'm sorry, Hammer. When I was first starting in the TE field, I would say Hummer all the time. I'm so sorry, Hammer. I'm sorry, Travis. Hammer. And I'm so glad this is being recorded now. Hammer is more sensitive than crossmatch, is more sensitive than RMBLAT. So take that into consideration. Yes, but yeah, so sensitivity, if you have some more sensitive search, it's generally a little bit slower. So there's kind of that trade-off. You can also, increase the batch jobs. You can make it a little bit faster if you have an increased batch number, and this will also be a little dependent on which engine that you select, search engine you select. In terms of sensitivity, I generally just do a -S for the most sensitive search. But again, if sensitivity isn't necessarily a priority, just want to get idea of repeats, you can change that parameter. And here are the rest of the options. Read that briefly. You have 5 seconds. So the main options are highlighted in blue boxes. You have contamination options, running options, and output options. Okay. I've highlighted some of the really common ones and underlined in green. So either have -lib, which is your custom library, or -species, which will do a lot, which makes a difference in how your repeats are processed, which we'll get to in a minute. I've also highlighted for the output options. You can have all kinds of options. If you want a GFF output, great. You want a cross-match like output, that's the default of RepeatMasker. If you want an HTML output, choose that for your option. Something I always recommend because it's so useful for downstream processing and all kinds, and especially if you want to create a repeat landscape, is to use -A, which will generate alignments, like the alignment file, and you'll be able to use those for so many different downstream things. Highly recommend it. It's not automatic. You have to say -A. Okay. Again, so there are 2 things that I want. Yes, sorry, this was in the previous image. I see frequently people say, "Oh, we don't want no-low. We don't want to mask low complexity repeats or simple repeats." Unless you've done this previously with a different program or you have a really good reason not to, don't even do this. Don't choose this option because you'll get false positives if you choose it. Okay, unless you have a really good reason to put this, not search for these, search for these, please. The other thing, and I will get into this in the output, the ID number in the very last column is really crucial. It's not just a placeholder for that line. It's really crucial for interpreting nested repeats and joining fragments. So unless you have a really good reason that way, unless a really good reason not to, I recommend always having the ID number. Okay. Okay, so for an example run, you should see this at the very top, Uppsala 2020 demo files. There is a 25 KB fragment of the chromosome Y assembly as part of the telomere to telomere project that is publicly available. So I'm not using something that's like private. And so in there is this 25 KB fragment as well as a library, because I'm gonna show you really quickly how to run with species and lib and show you the difference. And then we'll talk about what goes on with staging behind those searches. So for a command line, if you have your RepeatMasker, oops, I need to type the whole thing, RepeatMasker sensitive search, I want the alignments. And in this case, I want to indicate the species. Now I'm going to use human. So you can either type in human or use a quote and do Homo sapiens. Ooh, spell it correctly with the same matching quotes. Okay. And then obviously you'd want to indicate the chromosome or the sequence file. And sorry, genome, but sequence file you'd like to search for repeats. Okay, so if you go ahead and just run that, it will tell you what version of RepeatMasker. So it's a little different than what I had on my computer at work, the different version. So excuse that. So it'll say which version of RepeatMasker is running, the search engine, the RepeatMasker, the database. If you've done species, it's using the master database. That's part of the RepeatMasker installation. It'll show you the lineage that it's using, the taxonomic ID for humans, and NCBI taxonomy. There's a lot of information that's already here. You can know a lot of information, what libraries are being used. How would you identify this particular genome again for this taxonomy? And this takes a little bit. So we're going to let it run. So if you're using a particular, if you use that species and let's say there's some library that you have, it's EMBL format or a .h5 format. We talked a little bit about .h5 or HDF5, apologize, but the extension is H5. There's a lot of metadata and information included in H5. So if you want to download the DFAM database, H5 is the way to go. And this is probably going to take a little bit. Yes, this only happened once when it has to build the libraries. And if it takes, I don't want it to take too much longer, which is why I have screenshots. Okay, here we go. So you'll notice one of the things, let's Arian, it's not particularly this slow. It's because of the virtual machine. Yeah, so I promise Arian's program is not this slow to begin. But you'll see if there is multiple runs on the same genome and you want to do some different settings, make sure that you're renaming those files. But if to decrease kind of confusion, it will place older runs in their own particular file with a timestamp. So what you're seeing right now is you're watching the staging. Hey guys, it's a little distracting. I'm sorry. Thank you. So what's happening right now is you're watching the staging for the dash species kind of setting. Okay, and it's gonna finish soon. Right now it's refining. ALU subfamilies is a big part of the human portion, is refining these subfamilies, because I don't know if any of you worked with them. I apparently, you clearly have. I've worked with them, rather. Sorry. There's refinement at the end. Some of the subfamilies can be very closely related, so there's an alignment to any ALU subfamilies that occur, realignment. Okay, so you can see there's a lot going on in terms of staging. It's looking for simple repeats, ALUs, interspersed repeats of a certain length and age, and ending with another simple repeat batch. The very end with refinement. And the processing output here is part of ProcessRepeats. Okay. So that's with dash species. All right. So again, I've highlighted in the red, if you're going to run the same settings or on the same genome file in this case, it will move these files to another output. I'm going to run the same, using the same file, the genome file. But in this case, I'm going to use -lib, which is just the Homo sapiens library from DFAM. I have stripped the names from this to kind of act like it were the raw output from, say, Repeat Modeler. Okay, so because I want to show you the drastic difference in behavior for library species. Okay, whoop. Again, it's gonna luckily won't have to build the libraries again, but to kind of, while it's still doing its thing, if you look at the differences in terms of the processing output, there's many fewer cycles. So essentially what you have simple repeats in one batch. All of this library, this is the 1,356 human repeats, descendants and ancestors. And then you have another for simple repeats. This is in stark contrast to all of the steps previously. Okay, so I'm gonna go over a very simplistic schematic of the differences in staging. And again, once we get processing, there's only 2 cycles of those that process repeats. Great. So again, this is reflected in the output. Same here. Again, wasn't relying on the virtual machine. Thank you, Michele, but just in case it didn't work. Okay. So what is the difference? Why does it look so much more sophisticated, dash species versus -lib? Okay, for -lib, there are essentially 3 broad stages. The first is looking for young simple repeats. The middle stage is a competitive search with your library. That's it. All of them treated similarly. They're not been in the classes, all the same. And then you have an old simple repeat search. With dash species, and this specific example is for mammals. There's more sophisticated staging for primates and even more for humans. Okay, this was originally designed to look for repeats in the human genome. But this is for mammals. Again, you have the same simple repeat stage, but then you have cut libraries for signs, and then short repeats, and you have cut library, and then you have the mask library. But why cut library? Why does it even matter? Why is this different than -lib? Okay. So using staging, you increase the speed by decreasing the search space with each step. Younger elements insert to older elements, and without clipping, this is what the cut lib is, fragments of older TEs are not going to be detected. So for example, let's say we didn't have the cut library. You didn't cut out the younger TEs. This older TE, this small fragment, might not score highly enough when it's matching to a consensus, so it's going to be missed. You're going to get maybe this older piece of this TE, this bigger fragment, but not this little one. But if you have the cut library, and there might still even be a small gap, but the scoring matrices will allow to kind of bridge that small gap, and you'll identify the entire TE. So this is kind of the logic behind using staging and the power of staging, and the difference between dash species and -lib. Okay. At the very end of RepeatMasker, you saw all those cycles. So this is ProcessRepeats. Well, I'll get to that at the end. So it's an adjudicator and makes a call by sifting through all the possible alignments, which are in the .cat file. We'll get to that in a second, and trying to make one call when possible to try and just, okay, best scoring match. All right. There have been specific rules that have been built in based on expert knowledge. So for example, lines that are in blue are split into 3 different fragments when you're trying to adjudicate. Because the majority of the subfamilies have been generated using the 3' end of line, that's where you're going to essentially assign like a subfamily. So, for example, if you have 3 fragments that are overlapping, the 5' end, the ORF2 region, and the 3' end, let's say the 5' end and the 3' end are conflicting just a little bit. So L1ME. Can't think of a number. It's probably not real. ME4, and the 3' end is L1 ME5, ME5 will be prioritized because that's where the most information is, because lines are 5' truncated in general. Okay, so kind of those sorts of rules. If you have LTRs, there are many solo LTRs in the genome. Also, you can have strand switching and recombination events, trying to take into account the biology of these elements. Also, with DNA elements, you're going to have internal truncations. And so you're going to have these metadata tables as part of process repeats. It's like, oh, I should join this 5' and this 3' fragment into one to recognize that internal deletion, that deletion product. So this is what process repeats is doing at the end. Okay. We good so far? Everyone's somewhat following? Okay, I'm getting mostly nods yes. Okay, great. So understanding the output. All right. So there are 5 different outputs. I've highlighted 3 in black. We're not going to talk about the gray ones. So the .out file is what most people interact with. Yes, I'm aware that there's a lot going on here. All right. So just I'm gonna increase a little bit just to highlight what we would see with the dash species for human for this particular set. Okay. If you want to open on the command line, okay, I don't know why it didn't open. That's fine. This is why I have this. This is why I have my screenshots. So if you were to open this, like using less, opening the .out file, you would see a bunch of lines. Well, what do these lines mean? So the first column is the Smith-Waterman score. The second is the divergence, so it gets like rough age estimate. Then you have % deletion and insertion, and this is query relative to target. You have the query sequence name. In this case, it's the HG002 chromosome Y, the first 25 kilobases. The begin of in the query, where it matches to the repeat, the end, and then what's left over, what didn't match. The strand, C is complementary, so negative strand. Then you have your matching repeat, the class and the family, and depending on the strand, this column is either beginning to the match and the repeat, the beginning, or what's left over in the consensus of the repeat. A little confusing. The end, and the position in repeat, that's always the same. That is the end, matching the consensus. And the same, in this case, the beginning of matching the repeat is in this column, this 36, because it's on the complementary strand. But all the rest are positive strand. So the beginning is in this position in repeat, that is the beginning, and what's left over or didn't match the consensus is going to be in this left column. Okay. If you work with humans, or even if you don't, you've probably seen MLT1B or ALU or any kind of line subfamily. Okay. I think an underutilized column, personally, I think, is the ID column. So if you notice, you see the number 22 over and over again. So clearly not just a placeholder. What you can see is that actually what you have, L1MB2, L1MB2, L1MB2. So this gives you an idea that this is the same insertion. That's just the insertion number, not a line number. So this gives you nested repeat information. I'm just going to skip to the next slide really quickly to show you what I mean, what it would, in theory, what it looks like. I've highlighted just a small example to show that the red are the fragments of L1MB2 versus you have an LTR2C, but then you have ALU insertions inserted within the line sequence, within the LTR sequence. So this is the kind of information you can get from the ID number. So that's why I say, unless you have a really good reason not to include it, always include it in your output. If you don't need it, fine, but at least you'll have it later in case you change your mind. Okay. Again, back to the species-lib, you have an option to use species or -lib. For example, I just stripped away all of the information. Let's just say you have a bunch of FASTA sequences. You can't see any nested repeats, and the stars over here indicate that there was an incompatible annotation that could not be resolved by ProcessRepeats. You've taken away all the information and, using just -lib, none of the processing at the end. This highlights the difference. Okay, to be fair, I took the human and I stripped away information that we already knew. Okay, so this isn't, you're not going to get this as human output unless you really want to challenge yourself somehow. But kind of showing the differences in just the nested repeats for the ID numbers, because the DFAM entries have split by 5' end, 3' end, that's what you'll see here. Okay. Again, there's a lovely visualization for TrackHub on UCSC that should be able to implement soon. So this is why ID matters, nested repeats. If you're looking at you want to look at the alignments that are associated with the out file lines. The unprocessed file, all of the alignments are in the cat file. The processed, where it made the decision, is in the .align file. .cat, unprocessed, .align, processed. So for example, in this case, in the .cat file, it does not match with the .out file, but there's been that subfamily refinement for ALUs that took place that is in the .align, .out. Okay, so that's a difference. But if you want to see exactly how those are derived in some decisions, look at that. There's also some post-processing that you can do. There's build summary and then create repeat landscape. So build summary, if you want to generate this file, just put in build summary and your out file. That's it. That's all you need. To get even a bit more information, use your -genome file, which is either the 2-bit genome or a tab separated chromosome, size of chromosome. And you'll get this kind of information. To highlight the differences, you have your repeat class for the -lib. Again, all just unspecified. It does the breakdown of each of the families, but less information than if you were to use the -species. Very clearly separating. You also get a little bit difference in the amount of base pairs masked. You want to create a beautiful repeat landscape. 2 steps. You need the .align file, which is also why I recommend you keep the .align file. Again, it's just ProcessRepeats, typing in capital P, capital R, repeats. I'm rushing a little bit because we are getting towards the end and I want to at least touch on some of these things. You'll get your .align file. The output is a .align, .table, and .out. If you want to, I apologize, skipping a little. If you didn't originally generate your .align file, you can regenerate it if you have the cat file. You can do this. First, you have to get the divergence summary. So here's the summary file that you would name. Here's your align file. The output is going to be a divergence summary for create repeat landscape. For this particular run that I did for the alignment, it'll generate this image. Obviously, it looks a little bit different than the whole genome, but your HTML output, you should just be able to copy paste that into where you put the URL, and you should be able to see this. So this is just a screenshot of actually the file that I saved here. All right. So this is, probably don't have too much time for this, but this is, so I talked about the API for DFAM, like accessing that data. The other tool that you can use is FAMDB. And this might be a little bit what people are more used to accessing, how you access data or running programs. So FAMDB, you would access the data in an H5 file because it's very rich. Again, I'm going to go for the more rich data files. And there's a lot of information that you can get if you just want to have, for example, if you want to do just a search name, you can do names. Oops, no, don't do anything. You just want to search a name and you put in Homo. You're going to get everything from Homo sapiens to Thomo mice fulvus. Okay, so make sure if you want to do lineage in Homo, that's very different than just doing like a keyword search difference. So, Ari already talked about earlier about the differences between ancestors and descendants on the left. So this will show up if you do FAMDB lineage Homo with AD, which is ancestors and descendants. It'll show the taxonomic ID and CBI on the left, and the number of models at that particular taxonomic level on the right. All right. So if you want to get your own library or sub-library, this is how you would access it if you have something locally on your server. FamDB, families, that should be familiar if you remember from DFAM, accessing families on DFAM. If you want to do, this is your term, your search term in this case. Your format, let's say it's just a FASTA name. Come on, actually had this particular example in Slack, so I wanted to have this here. Including class in name, that should be a familiar format you're used to seeing with these rep-based library, RepeatMasker associated libraries like downloaded. And then I had AD again for ancestors, descendants. Okay. And the output that you should get, please, and thank you, computer. This is what you should get. If you have include class and name, this probably is familiar. If you do not have in class and name, you'll get this. It separates the name from the class, and this is a description field. Okay, so if you want to have that hash class, @ for taxonomic label, search stages, include class in name. Again, I will be distributing this presentation as well. Okay, I think I had 3 minutes left. Yes. Okay. So just to highlight one difference, if you're really interested in satellites. Is anyone interested in satellites? Okay. Oh, yay, some hands. Okay. So you might have noticed between different versions of RepeatMasker, it's before and after TRF was implemented. So you might have noticed before, and this is a toy example, so no one nail me to the wall if HSAT4 is your favorite and I didn't have the right simple repeat. Okay. So with TRF, it's essentially going to identify specific simple repeats in a specific order. I'm working with Nick Atlamos on this particular problem. Hopefully we kind of work around, but I don't know if you know what that is. He did satellites for the T2T human genome. So, a great guy. So TRF will show the simple repeat order. Previously, when it was based on consensus, you would have just HSAT4 and satellite. Now, is it true for HSAT4 satellite now? I do not know. I did not check. This is a toy example. But if you have this, like an older version of RepeatMasker, older output, and you're noticing this difference, this is why. Implementation of TRF versus previous consensus. And there is TRF is a great program in terms of analyzing and identifying simple repeats, but you lose that name for the consensus. Okay. And if there's some time, I'm happy to answer some questions. I'm actually ahead of time on this one. Yay.
Yeah, thank you, Jessica. Maybe a round of applause for the questions. I believe this is going to be very informative. And so if you have, maybe we can take one question.
Hammer will accept sequences, not just profiles.
Thank you, Travis. Thank you.
It's a very small question and a bit embarrassing because I've been using RepeatMasker since forever, but I don't know how to interpret the SW score. What's a good SW score?
So Smith-Waterman score depends on a bunch of different things. Smith-Waterman score is dependent on the length, it's dependent on gaps, it's dependent on the gaps and mismatches, and so a lot goes into it. So for example, a really high scoring ALU match, it's not going to score nearly as high as something that's a lot longer. So it depends on the size a little bit, and I can talk about the specifics of that calculation a little bit later.
They worry about the SW score.
Worry how? What do you mean by worry?
If it's low or high.
So generally false positives are going to be below, it depends a little bit on the match, but generally below 250 is a false positive. They're talking about the Smith-Waterman score and being concerned. Typically below 250 is false positive.
All right, I think we have to move on. Thank you very much. Yes, please, applause.